Hello there, and welcome back. In this video, we're going to start the beginning of a new journey in the realm of probability theory and its connection to statistics. Up to this point, we have mainly been focusing on discrete random variables for events, and usually we represent those discrete random variables by capital letter X. So as we already discussed several variations of them, probability mass functions represent the probability of those random variables. For example, binomial, Poisson, hypergeometric, multinomial, negative binomial, and several more can describe the probabilities of discrete random variables that have a variety of structures. And more importantly, the probability that capital X is equal to little x can be represented either in the event space, sample space perspective, or from the probability mass function perspective. So now that we have thoroughly discovered or explored different discrete random variables and their probability mass functions, now where are we going? So now the question becomes is what if x is not discrete but continuous? So now we're going to begin our journey of continuous random variables and how we can talk about the probabilities on them. So all of the functions that are going to be defined on continuous random variables are going to be represented as f sub x instead of p sub x, and this is going to be referred to as a probability density function. A probability density function, or in short, a PDF instead of a PMF for probability mass functions. So one sad part about probability density functions is that the expression f sub x of x, this is not a probability value. So this is not a probability value. So we cannot plug in a number x into this expression and get a probability number back. So for example, if I ask you what is the probability that you spend exactly 10 minutes in a store, you cannot just plug in 10 into this function and get a number. Because if x is truly a continuous random variable represented in time, the probability of spending exactly 10 minutes is 0. It's not the impossible zero number, it's the virtually impossible zero number, because technically if you try to measure your time that you spend, usually it's going to be like 10.000327 seconds, which we sort of round to 10, right? So we sort of approximate it with a discrete number even though it is actually a continuous number. So this, of course, creates one of the first issues on, well, how do we describe the probabilities of continuous random variables? So the first thing that we need to sort of discuss is, well, how does probability density functions represent those numbers, right? So let's just briefly talk about the basics of probability density functions, right? So let's assume that we are interested in, so let's look at a particular example. Let t be the amount of time, let t be the amount of time you spend on your cell phone every day. So since we're letting t represent the amount of time that you spend on your phone, t is definitely going to be a continuous random variable, assuming that we're not going to be rounding to, say, the nearest second or the nearest minute or something. So that means we can represent t in terms of its possible values to be lying in the range of 0 to 24, and let's assume this is in terms of hours, right? So t is a continuous variable defined on the interval 0 to 24. So what type of distribution might be associated to this random variable t? So let's just graph these values out. So little t is going to represent all of the possible values that capital T can take. So of course, some people might spend exactly 0 hours on their cell phone, and of course the maximum is going to be 24 hours here. This vertical axis is going to be the distribution of our time, and we'll sort of interpret what this means in a moment. But let's assume that most of our people are going to be spending somewhere around, say, 5 hours per day on their cell phone. So maybe the distribution maybe sort of looks something like this. Do people spend 24 hours on their cell phone exactly every day? I don't know, maybe, but probably, very unlikely, right? So let's just put it somewhere there. So this is going to be at least a model for the distribution of the time that we spend on a day. At least a randomly selected person spending time on their phone per day. So in order for this to be a probability density function for this random variable t, a couple problems need to be true about this graph. So the very first property that must be true is that f of t for all values little t must be greater than or equal to 0. So it always must be above the horizontal axis. And one of the reasons why we want this to be true is because we don't want negative probabilities. Um, because if you know anything about calculus, if we integrate a curve that's underneath the x-axis, then that's going to generate negative numbers. And of course, that leads into the second property of what a probability density function must satisfy, is that the integral over the support of this curve in terms of non-zero probabilities, so the area under this curve must be equal to 1. So what's this fancy symbol in case you're not familiar with calculus? So this statement here just corresponds to the area under this curve on the interval 0 to 24. Now this function might have, behavior outside of this interval 0 to 24, but we don't care about it because we're defining our time values to be on 0 to 24. So as long as the area under this curve on our region of interest is equal to 1, and this function is always above the x-axis on that interval, then this function, f of t, is a probability density function. So let's just formally state these two properties. So for all probability density functions, the following two properties must be true. So first off, the function value for the random variable x must be greater than or equal to 0, and this must be true for every value x in the support of x. And remember what the support of a random variable is. It's the set of all values that are possible, or of interest to us. It really depends on how you're phrasing these problems. And the second property is that the area under the curve over the region of support must be equal to 1, right? So for example, if I were to give you a couple functions, so let's assume that this is my PDF, and let's assume that this area here is my support. If this area is equal to 1/2, that's not a probability density function. And if you have another curve here, let's assume this is our curve, and let's assume that this is our region, so this point to this point. Is this a probability density function? So even if the areas of here and here add up to 1, since we have negative area here, this is not a PDF also. So two properties has to be satisfied. So if you have some curve over here, and you were to calculate the area under that curve on that interval, the curve has to always be positive and the area must be 1. If that is the case, then this curve here, f of x, can be represented as a probability density function for this particular curve on some interval, say a to b. Now that we know some of the basics of probability density functions, and you might be a little scared because now we're talking about some calculus, let's actually look at the very first probability density function where you actually don't need any calculus at all to calculate probability values on. The first probability density function that we're going to be taking a look at is going to be referred to as the continuous uniform distribution. If you remember when we first started talking about probability mass functions on discrete random variables, one of the very first distributions we were talking about was the discrete uniform distribution, which was defined on the interval a to b, where you do like a plus 1, a plus 2, a plus 3, all the way down to, say, b minus 2, b minus 1 up to b. So the distance for each of these points was going to be 1. And the probability that our random variable x could take any of them was equal to the same value. So if you have n different points on this interval, then 1 over n would be the probability. So the graph of this pretty much looks like a discrete rectangle, right? And it had an expected value and it had a variance, and we solved problems associated like rolling a 10-sided die, for example, or maybe even flipping a coin if it was a fair coin. Now for the continuous uniform, it's practically just a extrapolation of that. So we have a random variable x, and x is again going to range from a to b, but now we can take any value in this interval, either the closed interval or the open interval. Technically, it doesn't matter for the continuous case, and I'll let you think about why that is over the course of our discussion of continuous probabilities. So in order for this to be a probability density function on a random variable, so what are the properties? So this box has to be above the horizontal axis, which indeed it is, at least from this picture, and the area of this box must be equal to 1, right? So what is the height of this box going to be, right? And then that's going to give us a function that we can integrate if we want to. So the length of this box is going to be equal to b minus a. So in order for the area to be 1, remember area is equal to length times width. So the length is b minus a. The area is going to be 1. So we have 1 is equal to b minus a times the width, which means the width of this box, or the height of this box, is going to be 1 divided by b minus a. So that means 1 over b minus a is the height of this box. And that gives you the uniform distribution. Very easy to prove. Right? Continuous distributions are very easy to visualize in terms of the graph because we're not working on a discrete case. So let's look at a particular application where we can actually use this distribution to our advantage. So suppose that the bus arrives every 40 minutes to a bus stop and it is currently 1:30 p.m. If you have no idea as to when the bus last arrived, what is the probability that it will arrive within the next 5 minutes? So let's just draw a little picture on how we can possibly visualize this problem as a continuous uniform distribution. So let's just pick a time here. So t is going to be our random variable in terms of when it arrives. So right now it's going to be 1:30 p.m. And we know that the bus arrives every 40 minutes. So we're guaranteed that the bus will arrive 40 minutes starting at 1:30 p.m. all the way up to 2:10 p.m. Right? So there's a 100% chance that it arrives within this time. And now you can start to see how continuous random variables and areas in a curve sort of come together, right? So the area under this curve must be equal to 1. So what is the length of this box going to be equal to? So if we switch to minutes, that's clearly going to be equal to 40 minutes. So in order for this area to be 1, what is the height of this box in terms of minutes? That's going to be equal to 1 over 40 minutes, right? So this is going to be my vertical axis. This is my, that shouldn't be f of x, that should be f of t, right? Because we're using time as our variable. So what do we want to know? So what is the probability that the bus arrives within the next 5 minutes? So that's 1:30 p.m. to 1:35 p.m. So if we sort of draw on this picture, where is this area going to be? So 135 is going to be chilling somewhere around here. So we need to find the area of the region associated to this interval, right? So how can we find that interval? So that's going to be equal to what? So the length of that smaller box, that's just going to be 5 minutes, right? So that's going to be 5 minutes times the height of that box, that's going to be equal to 1 over 40. So the area of that little region here, that's going to correspond to our probability. That's going to be equal to 5 divided by 40, which is going to be equal to 12.5% chance. And that's, of course, assuming that we have no idea as to when the last bus arrived. And also, we know that it will guaranteed to come within the next 40 minutes, right? So there's a 12.5% chance of that occurring. So let's look at another variation of this problem. For example, what is the probability that it arrives after, let's say, 1:52 p.m.? So what is this equal to? So let's just draw a new box just to make our picture clearer. So what time is it now? It is, let's assume again, 1:30 p.m. and it's guaranteed to arrive by 2:10 p.m. And we want the probability that it arrives after 1:52 p.m. So 1:52 is going to be somewhere here. Let's draw our uniform distribution here. So we want to find the area of this box. So notice that this problem is equivalent to saying what is the probability that t is greater than 1:52 p.m. And in terms of this problem, notice that the probability that it arrives after 2:10 p.m., because we're talking about when it's going to arrive next, right, is equal to 0. That means this problem is equivalent to the probability that time is in between 1:52 and also 2:10. Now here's a question for you to think about. Does it matter if I include the greater than or equal to, or if I just use less than and less than? I'll let you think about that, at least for the time being. I'll answer this question eventually. But the answer is no, it doesn't matter. So what is the probability that it arrives in this region? So remember, what was the height of the box? Remember the length of the entire box was equal to 40 minutes, right? That means the height of the box was 40 minutes. So if that's the height of the box, what is the height of the smaller box? So that's going to be equal to 18 minutes. That means the probability that this occurs is going to be the length times the height of the box, 1 over 40. So that's going to be equal to 18 over 40, which is going to be equal to 45%. That means there's a 45% chance that it arrives after 1:52 p.m. or equivalently between 1:52 and 2:10 p.m. Now that we have a starting notion of probability density functions and calculating probabilities on these continuous random variables, now let us briefly talk about the expected value and the variance of continuous random variables. So let's consider again this same exact application, right? So if we have the same problem, so let's just draw this probability density function again. So this is going to be f of x. So our arrival time for the bus will be 1:30 to 2:10 p.m., let's assume. And we know that the bus will arrive within this time period somewhere, right? It's not exactly a box, right? I didn't really line that up very well, did I? So let's just line that up just for the sake of clarity, right? It's not so much better, but it's definitely better than before. So we know again that this area is equal to 1, right? So that makes it a probability density function. So let's ask the question, what is the expected time that the bus will arrive? Now, without me giving any formulas, what number makes the most sense in terms of the expected value of this random variable? If you remember from the discrete case, the expected value of that random variable was exactly in the middle of that distribution, and it is exactly in the middle of this distribution as well. So the mean of a continuous random variable will still have this measure of central tendency representation. So let's just summarize those theoretical properties for the continuous uniform random variable. So generally, the density function for a continuous, the uniform random variable, has the probability density function 1 over b minus a for all values x between a and b, and it's going to be equal to 0 otherwise. So outside of the 130 window, so everywhere over here and everywhere to the right of 210, the probability is going to be equal to 0 because we're focusing on when it comes next. The expected value of this random variable is going to be equal to a plus b over 2. So that's the same as before, but the variance is going to be slightly different. Now, one question, well, how do we actually calculate the expected value and the variance of a continuous random variable? We haven't exactly talked about that. We know how to do it if x is discrete, but what if x is continuous? So let's just briefly, review for discrete case. So for discrete random variables, the expected value is going to be the sum across all values x in the support of our random variable of x times our probability mass function. And of course we can calculate the second moment and then the variance from there, right? So for continuous, we're practically going to have the same representation, but instead of summing, we're going to be integrating across all values x in the support. and it's going to be x times the probability density function. Similarly, the second moment of a continuous random variable is going to be the integral across the values x in the support of x squared times fx of x dx. And lastly, if I have the expected value in the second moment, how do you think we're going to find the variance? Take a guess. This is going to be equal to the variance is equal to the second moment minus the mean squared. Now, just a heads up, I will eventually start switching to software in case you don't know how to use or do integrals, so that's not going to be that big of a deal. But for those of you who are calculus aware, let's just work through just a proof of how to show that the expected value of a uniform random variable in the continuous world is a plus b over 2. And we'll also go through the proof of the variance of x equal to b minus a squared all over 2. So if you do have some calculus background and are curious of how these formulas sort of come up in the realm of these new formulas, I will switch the colors back around to a different color, so you know where the proof ends and where it starts. And if you're not interested in the proof, then you can skip ahead later in the video where we discuss just a couple more things that are important to know about continuous random variables. Enjoy. want to close out this introductory lesson on continuous random variables and probability density functions with a question whose answer should be very obvious. Does a probability density function need to be uniform, i.e., does the shape have to be a rectangular distribution for which we can easily avoid using calculus on? And the obvious answer should be no. The next shape that probably would be the easiest to calculate areas on would be the area of a triangle, which is associated to a trend that is linear. So let us assume that the amount of time x a person wants to spend on an exam follows the following linear trend. So we have a decreasing linear trend. So the majority of people probably want to spend 0 minutes on an exam, or maybe not, but let's just assume this is the case. And of course, 120 minutes, nobody really wants to spend 120 minutes on an exam. Most people probably just want to, not take it at all, right? So the majority of people should be situated near 0 minutes, and practically no one should be situated around 120 minutes. Let's at least assume this is the case. So, how can we find the area of the triangle, or how can we make a probability density function based upon this? So let's just go through that motion. So we want this area to be equal to 1. So what is the area of a triangle? So that's going to be 1/2 base times height. So the base, at least for this, is going to be 120 minutes. That's 2 hours. Let's assume that's like the maximum time you can spend on an exam. So what does the height have to be equal to? So we want the area to be equal to 1. The base is going to be equal to 120, and the height we're looking for, and this is going to be equal to 60h, and 60h must be equal to 1. That means h is going to be equal to 1 over 60. Ooh, a fraction, right? So that gives us at least something to work with. But what about the equation of this line? Because we need to find the height of this curve at a bunch of points, that we need to know the area of a subregion, for example, right? So finding the equation of the line probably is the next thing that we would need to do. So this line passes through the points 120, 0, and it passes through the point 0, 1 over 60. So using these 2 points, we can find the equation of this line to be equal to 1 over 60, so y2 minus y1 all over x2 minus x1, and that's going to come out to negative 60, actually no, negative 1 divided by 60 times 120, which is going to be negative 1 over 7,200, right? And we already know our y-intercept is equal to 1 over 60. That means the equation of this line is going to be equal to y equals, actually this is going to be my density function, right? So this is going to be equal to fx of x is equal to negative 1 over 7,200 x plus 1 over 60. So this is my density function, right? Now just take a moment to appreciate, or maybe not appreciate, that I've just increased up to a linear function. So calculating areas under curves already is becoming a lot more tedious than just the uniform rectangular distributions would be. So if you didn't have any alternatives, well, what could you do? And what type of problems could we solve with this? So let's just give one basic example. So let's select one person at random. So let's select one person at random. What is the probability? What is the probability that they want to spend between 20 and 30 minutes? Now you might not want to do this by hand, but you at least should have a conceptual understanding of where this area is located, right? And then you can use software to evaluate it for you, right? So here's our probability density function. So that's going to be fx of x, right? And we want the probability that we're between 20 and 30 minutes. So remember, our upper bound is 1 in 120, and our upper bound is going to be, our lower bound is going to be equal to 0. And we want this area here, where this is 20 and this is 30. So we want to find the area under the curve on this region. So what shape is that? That's the area of a trapezoid, right? Now, how do you find the area of a trapezoid, right? So maybe you remember, maybe you don't. And that's going to be equal to 1/2. So I'm going to call this height base 1, this base 2, and I'm going to call this the height. So it's sort of a trapezoid turned on its side. And that's going to be 1/2 b1 plus b2 times h, right? So if you actually use these values, so this height is going to be equal to f of 20. This other height is going to be equal to f of 30. The height is going to be equal to 10. That means, according to this formula, this is going to be equal to 1/2 times f of 20 plus f of 30 times 10. So how do I find f of 20 and f of 30? Well, I'm going to take these numbers, 20 and 10, and I'm going to plug them into x, and I'm going to work out some nasty fraction math, right? Um, I'm not going to work that out for you, but of course I have the answer for you just in case you are feeling adventurous. But the probability is going to come out to 13.19% percent chance of that occurring, right? So if I choose a random person, 13% chance that they're going to want to spend 20 to 30 minutes. Definitely if you choose something a little bit more closer, for example, what is the probability that somebody chooses between 0 and 5 minutes? It's possible, it really depends on the shape, that area is going to be a lot larger. For example, if I go from 0 to 20, it's possible that area is going to be larger than that orange region, right? And you could find that out if you want to. But notice that the complications of the mathematics associated to these problems gets very difficult very, very quickly. And let us assume that this shape is completely bizarre, right? Let us assume the density function is like, something like that. Like, do we have a cute formula for finding the area under that curve on any particular interval? Most likely no. And even if you do know calculus, it's not even guaranteed that that integral actually has an antiderivative for you to plug answers into. So for the most part of this series, at least, we're going to be using software to calculate these integrals for us so that we can just focus on the statistics and the applicational use of probability. So for this introduction, I'm just going to end it there. And in the next video, I'll actually go through a quick overview of how you can use a software to do some of the basics of probability density functions so that we can actually focus on the interpretations and not necessarily the underlying mechanical math that is associated to it. So I hope to see you there. Take care.